Hey there, everybody. Welcome back. This will be our final video for 13.1. It's on multivariable substitutions and maybe trying to pick graphs from what we see like contour lines. So we're going to start with, well, maybe I should cover it up a little bit, make it a little bit easier to follow. We're going to start with f of xy equals y squared. I'm sorry, f of xy equals y squared x e to the xy. But we have two other functions. U is also a function of xy, so is v. U is y squared ln of x, and v is y to the negative 2 cosine of x, or cosine x over y squared. And what we're going to do is we're going to write f of u comma v. So the way you go about doing it is everywhere you see in f of x, y, and x, you plug in a u. And everywhere you see a y, you plug in a v. So I got v squared u equals e to the uv. And now we are going to substitute in everything for u is y squared natural log of x, and everything for v is cosine x over y squared. When we do that, it gets a little messy, right? I recommend writing it slowly when you're doing a substitution like that. So just plug in everything without trying to fix it or condense or simplify. So that's what I have there. And then I look at starting to condense. So I square everything on the inside here, y to the negative 4th and cosine squared x. This one didn't change. I didn't change this yet because I'm going to combine these as best as I can. Y squared and y to the negative 2 offset each other, and we have e to the ln of x cosine of x. And going down to the next one, we combine the y squared and y to the negative 4. We get y to the negative 2 there. Cosine squared x, natural log of x. And then what did I do here with ln of x cosine of x? Recall that any constant times natural log of x can be written as natural log of x to the r, like that. Well, my cosine x just happens to be on the right side rather than the left side, but we can move that in as an exponent. Why would I want to do such a thing? Because I get e and natural log there, and they offset each other, so we can get rid of them, make it a little bit prettier. And we just have x to the cosine x from that part. And then we have the cosine squared x, natural log of x, and I move the y to the negative 2 to the bottom finally. The next thing we want to take a look at is some images and try to figure out what matches with what. This is a little hard to do with Zoom, but we'll make the best we can of it and just try to look at each one individually. So we have some weird graphs up here, and we have some weird contour lines down below. Okay, so it might help to pick or look for what's what here. Ones that might be easiest to pick out might be the 4 spikes here, right? I see 4 spikes, and I only see one region that has 4 spikes. So that one, graph 2 and graph C match up. And then when we're looking for other ones, it's worth noting that when the height drastically increases, or yeah, there's a drastic height increase as it close to each other, it means closer rings. We saw that on the half dome when you went up from z equals 4, where it was on the very xy plane. Z equals 3 was 3.87 rather than 4 radius. The dome was almost vertical right there, and so it was a drastic height increase without going inward much. So we're going to see close rings. So what else can we do right here? Well, this one's got a bunch of, it looks like an egg crate, a bunch of spikes there. And this one's got a bunch of little spiky areas with circles. So this one and this one probably match up, D and 4. And what else can we do? Let's see, this one looks like it's got regions. I got a ring right here, a big ring, and then there's a drastic dip. So they're going to have a bunch of tight circles. And presumably it looks like it flattens out, but because then the ring comes back up. And at the top, there's another little flattish looking area. This looks like a big circle within another big circle, which might be this one right here. So B might match up to 3. What other things can we match up? We've done these 3 right here. Let's see. The spike. Where might the spike be? Well, we've got it. It goes really high really quickly, and there's only one area. So we should have, when it gets to that area, really tight circles. But outside of that area, really wide circles. And so I'm looking at B, like it's not drawn into the same scale, I don't think, because that's a small spike. And so I think they zoomed in some. But we see really, really small circles or ellipses close to here. And then as we go out, it gets much wider. So I'm thinking F is V or 5. What else do we do? We've got 2 more to do, these 2. And what graphs do we have left? We have that one and that one. A little hard to pick here, isn't it? This one's got more like little wavy things, and they looks like it might go something like it's dipping down. It looks like this line, if I followed it along here, it dips down and comes back up. And this one over here dips down and comes back up. And there's regions in between where it dips down a little bit more. But maybe if I were looking at it a little bit differently, I don't know. I'm getting, if I had to choose between this one and this one looks more like this, but let's check the other one. Let's check A. We got the monkey saddle. The region in the center area is relatively flat. It's only when it's getting to the edges that it drops down low or goes up high. So 1 doesn't really have a relatively flat region in the middle, but 6 does. So I think 6 goes with A, and that's going to leave E to go with 1. That's it for 13.1. The next section has limits and continuity in multivariable functions. And guess what that means? That means delta epsilon proofs. If you've never seen it before, I will try to do some videos in 2-dimensional space before I shift to 3-dimensional space. Peace.